Now, if we compile this file, we would get a header file which is based on UFC, so it's completely compatible with UFC. But the classes which are derived from UFC should be initialized with a POM object. I'll explain this class later. This is a class for handling these extra degrees of freedom. Now, so for example, the classes that we have, the class which is derived from UFC DAF map, UFC cell integral, and also new class that we have here, they should be initialized with POM objects. If we have a couple of domains, for example, if we have a Poisson, we just give one object to this function. But for example, if we have elasticity, we should give two objects, which each field actually represent with discontinuity in each field represent by one POM object. And it's also worthy to mention that this header file is completely independent of the surface that we have represented. So everybody can implement its own surface function, and it's completely independent of header file. But we have two K classes which user should interact with this in main file. The first one is surface class, which represent the physical description of the surface, and the second one is POM class. Surface class, these are the main stuff that should be done inside surface class. The first one is finding the intersection points with the underlying mesh. Then we should determine whether a cell is crossed by surface. If a cell crossed by a surface, we need to have a specific, a modified type of quadrature scheme. And we also need to compute the ratio between the volumes of an intersected cell on the either side of the surface. But this is necessary to some implementation details. And POM class. The POM class, which is the main class that we pass to our linear form and bilinear form, has these three main activities. The first one is the evaluation of the Heaviside function at arbitrary points. Then, for the cells which are intersected, we need to compute new quadrature scheme. And the most important part is determining the enhanced degrees of freedom. Now, this is our solver environment. Now we have compiled our header file. If we include this file in our main in solver environment, so the first line is the function space for the function space, the standard function space. Then we got the DAF map from this function space to use this DAF map to create our POM object. And here, this is a definition of surface classes. As you see, these are the functions which we can represent the discontinuity shape. And these are the start point and end point of the discontinuity. This is for 2D problems. So for 3D, for discontinuity, we need just to define the discontinuity with two functions. And we have our POM object here. Then, and so based on this discontinuity vector, we can create our POM object and create a vector of POM object. Then the new function space that we have for this problem also receives POM object here. Then based on this function space, we define our linear and bilinear form, our variational form to solve the problem. And at the end, we define this, the object of this class, which to interpolate our result to continuous space. So this is just for visualization purpose. Now we have this domain with this crack inside, and u equal to 0 at the bottom and u equal to 1 at the top. So if we solve this problem, we have such a contour. As you see, we can also define a curve discontinuous easily by just defining a function. And another important aspect is using this approach in modeling of coupled problem. Because we can have different combination of continuous, discontinuous spaces. One of the advantages of automating this, it helps us to easily solve the problems with different discontinuous, with different combinations. For example, here we have two different states. One is continuous pressure and this continuous pressure and displacement fields. So this is case 1, and case 2 we have just discontinuous pressure. We have just discontinuous displacement, and pressure is continuous. So now this is our linear form and bilinear form for incompressible elasticity. And as you see, these are all standard terms that we have. And this is the integration of our discontinuity surface. Now, for the first case, where we have discontinuous field in U and P, again, like the previous one, we define our continuous discontinuous elements. Just add this together. We have a field for displacement, function space for pressure, and Taylor-Hood element by adding this together. So this was the first case where we have U and P both are discontinuous. And the second one is the case which actually U just is discontinuous, but P is continuous. The only difference between these two files are just these two lines. So all the rest are same. So with changing a simple line, we can just solve two different problems, which if you obtain them manually, actually they are completely different. And this approach can be also used in the modeling of crack propagation. This is a unit cube with this initial crack. So just here we just propagate crack in the arbitrary direction. So now we reach the surface here. But concluding remarks, we could extend FEniCS project for the PDEs containing discontinuities. This approach could decouple PDEs, implementation, function space, and surface representation. As a future work, because I have introduced new functionalities inside FFC, and since FFC, we even introduced UFL, I should also introduce this functionality inside UFL. The other point is optimizing this generated code, and I'll also use this approach in modeling of failure in porous media, and also flow transport in the fracture reservoirs. And these are the actually main challenges now I have to continue. Thank you for your time.